Hello sir, this is Bhavya Jha and today I am here to give a video presentation on the basics of quantum communication. Um, so let's start. Outline. So slide 3 is going to contain introduction to quantum communication. Slide 4 will be about key principles of quantum mechanics. Slide 5 will be about how quantum communication works. Then quantum key distribution, advantages of quantum communication, limitations and challenges, real world applications, and finally we'll be having about future of quantum communication and conclusion. So moving on to introduction. Quantum communication is a modern communication technology that uses quantum mechanics principles to transmit information securely. Unlike the classical communication that uses bits, that is 0 or 1, quantum communication uses qubits, which can exist in a superposition of states. So basically the goal is to achieve ultra secure and tamper proof data transmission that cannot be intercepted without detection, and that is the reason why we use quantum communication when compared to classical ways of communication. Now let's understand about the key principles of quantum mechanics. So the first one is superposition. Now a quantum particle can exist in multiple states. It could be 0 and 1 simultaneously. Then we have second as entanglement. So two particles can remain correlated regardless of the distance between them. And finally, we have the measurement effect, that is observing or measuring the quantum system disturbs its state. So these three principles are the foundation of quantum communication systems. So now, how quantum communication actually works. So quantum communication relies on qubits, which are the smallest unit of quantum or quantum communication, usually represented by photons. Information is encoded in quantum states, such as photon polarization. During the transmission, any interception changes the state of the qubits, alerting the sender and the receiver. So a secure communication channel is established only after verifying that no interference has occurred. Now let's understand about quantum key distribution. Quantum key distribution is the most widely used application of quantum communication. Example is the BB84 protocol, which is developed by Bennett and Bresard in 1984. That's why the name BB84 protocol. So QKD allows two users to create a shared secret cryptographic key using photons. So what happens is if an eavesdropper tries to intercept the key, the disturbance is immediately detected. And QKD ensures unconditional security based on the quantum physics rather than the mathematical complexity. So the difference between the classical quantum key distribution and this BB84 protocol is that during the classical transmission of data, whether a third party is able to access the data completely depends upon the computational power. But when we come to the quantum key distribution or BB84 protocol, this is a completely safe protocol because it creates a shared secret cryptographic key which is used only by the sender and the receiver. So no eavesdropper can get the message or have access to it because the quantum changes its state and the information is lost. And even the sender and the receiver are alerted that somebody is trying to eavesdrop them. So the advantages of quantum communication. So quantum communication provides unbreakable encryption using the laws of the quantum mechanics. So we discussed about the three like fundamental principles that were used. So those were nothing but the quantum mechanics that are used, and it detects eavesdropping attempts in real time, enables quantum teleportation, that is transferring the quantum states without any physical movement. It supports the creation of a future global quantum internet, and it's resistant to computational attacks that could break the classical encryption. Moving on to the next slide, limitations and challenges. So there are a lot of limitations and challenges obviously because right now quantum technology is just a hypothetical concept, even though there were certain companies that were able to provide the proof of concept, but it's not completely implementable right now. So obviously there are a lot of limitations and challenges that we face. So the limited transmission distance due to photon loss and noise in optical fibers is one among them. It requires quantum repeaters, something which is similar to amplifiers in optical fibers, so which are still under experimental development, the quantum repeaters. High implementation costs due to complex hardware and cooling systems. Environmental sensitivity. So quantum states easily degrade due to decoherence. So decoherence is the phenomena of quantum like qubits to lose their state of coherence. So that is called decoherence. And scalability remains a major challenge for global deployment, obviously. So these were the limitations and challenges of quantum communication. Let's discuss about the real world applications as well. So secure communication in defense, banking and government sectors, because it provides, as we previously discussed, it provides like unlimited security, and quantum satellite networks such as China's Meteus satellite enabling intercontinental quantum key distribution, protection of financial transactions and national security communications, research collaborations by companies like IBM, Google and NASA on building quantum networks, and future potential for secure cloud computing and data centers. So these were some of the real world applications of quantum communication. And let's discuss about the future of quantum communication as well. So integration with emerging technologies like 5G and 6G networks, development of large scale quantum internet linking multiple countries, quantum repeaters and memory will extend the communication range. Global research aims to create fault-tolerant quantum networks and expected to revolutionize the cybersecurity and data protection in the next decade. So this was about the future of quantum communication. And let's come to the conclusion slide now. So quantum communication represents a revolutionary step towards secure and efficient data transfer. It leverages fundamental quantum properties to ensure information security beyond the classical limits. Though challenges remain, advancements in research are rapidly paving the way for practical applications. In the future, quantum communication will form the backbone of secure global networks, which will definitely usher a new era of information technology. So with this, I would like to end my presentation, and this was about quantum communication, basics of quantum communication, presentation by Bhavya Jha from the Department of Computer Science and Engineering, bearing the roll number 234G180525. Thank you.